Yeah, I'm happy to introduce Dr. Gayle Woloschak, who's a professor of radiation oncology at Northwestern University's Feinberg School of Medicine and associate dean of the graduate school at Northwestern. She has a PhD in Biomedical Sciences and a Doctor of Ministry in Orthodox Christian Theology. She's active in the radiation community, serving as a member of the U.S. delegation to the United Nations Scientific Committee on the Effects of Atomic Radiation, scientific vice president for the National Council on Radiation Protection, and co-chair of Committee 1 for the International Commission on Radiation Protection. She teaches courses related to theology at Lutheran School of Theology, Chicago, and St. Sophia Ukrainian Orthodox Theological Seminary. And somehow, doing all of that, she's also managed to publish over 250 papers and edits several journals. So, welcome, Gayle.
Thanks, Dan. Thanks for that kind introduction. I'm really excited to be able to present this. Let me do my share screen. I do want to mention before I get started that last night I had the privilege of attending the John Templeton Award ceremony where my patriarch, the ecumenical patriarch of Constantinople, received the award, and it was a remarkable event. So it kind of sets my tone for today and makes me feel more optimistic than I usually would. Um, okay. As was noted, I do a lot of work in radiation biology. I have some other interests in the lab, but this is probably the thing I've been working on for most of my career in probably the last 20 years. Um, we house at my lab the Northwestern University Radiobiology Archives, which is the largest archive of tissues from irradiated animals in the world, excluding humans. There are other archives that manage humans. We don't do that. So my key points I want to make today, and I hope they make some sense, and I'm kind of bringing them up in a climate that is unusual right now. So first of all, radiation is a part of our environment. Second of all, we've learned a lot about radiation and particularly its effects, which is what my major focus on is the radiobiology. What are the effects of radiation exposure? And what we've learned from incidents and accidents that have taken place. The third thing is that we've harnessed radiation to use it to serve humanity. We use it for treating disease. In fact, I live in a radiation oncology department where we treat cancers with radiation. We use it for diagnosing disease, and I work a lot with radiologists who use it for MR, for CT scans and things like that. And we use it for providing energy, but sadly, we also use it for creating nuclear bombs and other bad consequences. The next point I want to make is that we have learned how to use radiation safely, but following guidelines has been very important for that process. So the safe use of radiation has involved developing guidelines. I belong to several groups, as was noted earlier, the National Council on Radiation Protection, International Commission on Radiation Protection, and the UN Scientific Committee on the Effects of Atomic Radiation. And our job is to help shape those guidelines that allows us to deal with radiation safely so that we've had very few accidental exposures that were not incidents created by humans. Changing the guidelines without careful assessment can be dangerous, and I will bring up the fact that our current government is looking at doing this, and there can be some real consequences from it. And my final point is that nuclear power is here to stay. There are really few options that can handle the large energy demand of our society. And I believe that AI, which requires large amounts of energy, is part of what's driving a lot of interest into further development of nuclear power. Okay, so let me start out. Radiation is part of our environment. This is showing the nuclear power plants that are making that use radiation and have radiation as a byproduct, but that's not what I mean. That's one part in which it's part of our environment, but more importantly, it's part of how we live. So in our ground, we have uh, we have um, a lot of thoron and radium, and that makes for large amounts of radiation. Our largest amounts of radiation are from uranium out here in the New Mexico, Arizona, Nevada area. Along the southern coast is and the eastern seaboard is where we have probably the lowest amounts of radiation. And here in the Midwest where I live, we have sort of moderate levels. I will also say that if you were to superimpose a cancer incidence map on top of this, it would be the exact reverse. The highest incidences of cancer would be down here and out here, and the lowest incidences would be out here. What that suggests is that radiation is not our major source of causing cancer in the US. This is another map. It's a little bit better done. It includes also Alaska, which I didn't want to leave out, and then some areas of Canada are included in this map. But you can see it's much the same. Highest areas here, lowest areas down here. Now, where does then our human-made contribution for radiation come from? Right now, this is the human-made part here. This is the part that's coming from our natural environment. Our natural environment is going to be what we find in the Earth's crust, what we get that comes through from space in our environment, what we ate today. So, for instance, if you had a banana, you had some radioactive potassium, and then also the some terrestrial background as well. Where does about half of our radiation, and maybe a little more than half, it comes from medical exposures. So CT scans, nuclear medicine, conventional radiography. Some consumer products like computers produce a very low amount of radiation, and some things like moisture density gauges and our devices that we use for smoke detectors also contain some small amounts of radiation. And then there's the industrial and occupational use. So, as I said before, early on it was thought that that only 18% was man-made and 82% was natural background. Now, with the newest way of looking at it, it's much increased for our medical exposures. I also do some work with lunar and Mars expeditions, and we do think about the radiation climate on different planets, and it's really very different on the moon than it is here. In fact, the moon has been totally mapped, and we recently mapped Mars, and you can see that Mars also has a radiation climate that's very different from Mars. So, and the astronauts, when they go through space, will have large exposures as well. Okay, so that sort of says that's what our background story looks like. What have we learned from radiation incidents and accidents? This is sort of a historical chart. X-rays were discovered in 1895. Radioactivity was discovered a year later. We started during World War I to have diagnostic X-rays that became commonly used. We thought about radiation protection. And in 1921, we have radiotherapy that's being used for treatment of cancer and other things, including inflammation, and that's become a recent story, is using radiation to treat arthritis in some examples. The nuclear bomb period occurred in 1945. We now have the ability to deliver therapy with a cobalt-60 instrument, which was novel compared to what was being used before. We have a linear accelerator that's developed. We have interventional radiology where we're injecting radionuclides into people to treat them for cancer locally. CT scanners come up for the first time in 1972. We have proton therapy in 1989, carbon therapy in 1994, a new technology called flash technology, and now we're doing combined exposures with other genotoxic agents. So this is sort of the history for where it comes from. Let me just show a few pictures to put this in mind. This is Roentgen, who discovered the X-ray. In Germany, there's actually a museum in Würzburg, Germany, if you get the chance to go. It's really cool to see a lot of these instruments that they had. These were the early devices that created X-rays. The problem was nobody understood the dangers from these instruments. They were low energy, which meant that they couldn't really be used that well for treatment. They couldn't penetrate very deeply in the body. They had no shielding, so when a person was exposed to this radiation, they got it. They got it everywhere, and people thought it was cool because they could put it up and see through their hand. And so it was sold like in just marketplaces. People could go and buy an X radiator and play with it at home. Since then, we've learned a lot, and we've learned that we have to regulate it. In those early days, there were a lot of people that had skin burns. There were people who lost fingers from it. There was an agent that was used that had radium infused water was used in the U.S. up until the 1920s for just general good health. So during this period before the 1920s, we really didn't understand the toxicities and the damage that occurred from these effects. Probably when we became most acutely aware was in the 1920s. We started to be able to measure radiation for the first time, but it was the development of the nuclear bomb that changed everything. There's a guy named Nolan who wrote a really great book called The Atomic Doctors. His grandfather was one of the physicians who dealt with the people who were exposed to radiation in the course of making the bomb. I was part of a committee this past year that went round to the Manhattan Project sites and looked at old records to try to identify how many people were exposed, what kinds of exposures they had, how many went on to develop cancer. And it was kind of so this is the picture of the first bomb. It's called the Gadget. It was put into a tower. It was set obviously to be able to explode when the time came. Here is the nuclear explosion that happened at the Trinity site in New Mexico in the US. So this is like just 0.025 seconds after it looked. The power of this bomb was amazing. It changed the way people thought. And here it is 10 seconds later where you can actually see the characteristic mushroom cloud coming up. Just for fun, my lab did a tour. The Trinity site is available. It is open 1 day per year. It's actually a national park. We went out there to see the site, to see a lot of the interesting things that are associated with it. This marks the place where the bomb was blasted. We actually, of course, took our Geiger counters and we're looking out here for radiation. It took us about a good hour and a half to get in that day, but I really advise people, if you want to know, if you're interested in it, it's really a cool site. They actually have the place where the plutonium was loaded into the bomb. They show you the farmhouse where it was built. They show you the remains of the place where they watched the bomb, which is remarkably close, if you ask me. But it's very interesting. And of course, there's the other side of the bomb. So there's the side where we made it, and the side where our people got sick from making the bomb. And I could tell some stories about that, but I don't have that long a time, so I don't want to talk forever. Here's a map of Nagasaki where we see the other side of the bomb, the effects that happened to the people in Japan for this exposure. This is the hypocenter of the bomb right here. It's called a hypocenter because it blew above ground and caused all the problems. These are then the dose rings for the distance from the site. And what you can see is that the city was very densely populated in that area. There was a river that ran through, and so there was massive impact. This is a map of not a map, this is a photograph of the devastation of the bomb. I actually got this from the Peace Museum in Hiroshima, but it's a map of an image of Nagasaki. And what we learned from this is that there were a large number of people that, of course, did not survive the explosion. Many people left. The infrastructure was totally gone. So these are people that are treated, that had exposure to radiation, but they actually never got any medical care. What we do today is we give people medical care, obviously, and it changes things. But the devastation was immense. Nobody had any idea of what to expect. Even after our studies here in the US, we really didn't know that much of what to expect. This is Nagasaki today. I took this out of my hotel room. This is about where the bomb would have dropped. And the thing to notice is that there are mountains that surround Nagasaki, and the mountains are were probably protecting a good part of the city from radiation. I'm actually a member of the scientific advisory committee for the Japanese atomic bomb survivors from Hiroshima and Nagasaki. I go there once a year, and we look at what's being done with the data from the patients that were treated following exposure or that were exposed. It's the largest population that has been exposed in the world to radiation, and there have been followed carefully by treaty between U.S. Department of Energy and the people of Japan, and so we've been following them, 120,000 people. I met an atomic bomb survivor. His name is Kodama, and he wrote a book about his experience. Hibakushu is the word they use in Japan for atomic bomb survivors. And as you can imagine, these people are very much uh, there was a lot of embarrassment for them. They felt a lot of shame that they had been exposed. They had lesions on their skin and elsewhere. Kodama himself had 6 cancers. I met him 3 years ago, so he was still alive 3 years ago. And I was kind of interested because he seemed to feel no ill will. He gave me his book, he autographed it for me, and we had a really beautiful conversation for a while about it. And he was excited that people continue to study the population. So some conclusions that we can draw from this are that there was a uranium bomb was dropped in Hiroshima, plutonium bomb was dropped in Nagasaki. And as I just said a moment ago, this population is very critical for us today. We use most of our estimates of how radiation is damaging, how much harm it does, by studying this population. Now, of course, what are the limitations? These are Japanese living in the 1940s. How much do they apply to us now? How much do they even apply to Japanese populations today? Is hard to estimate. And so there are many other populations that we continue to study, but this is the most important for determining our risk estimates for radiation. And the survivors and their children and grandchildren are being followed in this combined study from the US and Japan. It's done with the at the what's called the RERF, the Radiation Effects Research Foundation. And as I said, I'm on their advisory committee. So of course I have to show you at least a little bit of data, but I promise to make it simple. This looked at the dose versus the risk for getting cancer. These large bars are the error bars for it. And of course, as the dose went up, the risk came up, except for this little bubble here, which we think we can explain it, but it's not clear, and the error bars are actually quite large. But this becomes part of the problem, is this region down at low doses. You see that there's a lot of confusion here. You can tear this apart and look at it in more detail. But what this basically says is that at low doses, we actually don't know what's going on. And this gives rise to the huge controversy that exists right now, which is, what model do we use to protect people from low doses of radiation? And I mean, what are most of our exposures? Occupational exposures are all low dose. What you get from a CT scan is low dose. So, this has become an issue for people and has been controversial. So this is sort of the way we define this, is that we know here that, so here's the dose against the risk of getting cancer. So we're looking at excess cancers that we would normally have. This region above a dose, it's called 100 millisieverts. It doesn't matter what you call it. It is anything above this. We have really good data from atomic bomb survivors and other survivor populations to say what that risk is. Below 100 millisieverts, we have no idea. What we do by convention is we extrapolate and make it be a linear non-threshold response in order to be safe. We have molecular data, we have animal data, we have human data at these low doses, but to get the statistics we need in order to actually identify what's real is very difficult. There are some data that show that it's worse at low doses than it is at high doses. There are some others that say that it's better at low doses. There are some that say that there's a threshold effect. And then there's some that say a little bit of radiation is good for you. Go sit in a radioactive spot and lap up those rays. And the truth is, I can find almost every one of these responses depending on what I'm looking at. For this hormesis, this benefit, there seems to be a tickling of the immune response that makes for a benefit. There are some I can talk about that show a threshold. But the problem is, if this model, if you get a little bit of cancer at the same time that you're getting your immune system tickled, then you might want to think twice about whether you want to go get your immune system tickled in the exposure to radiation. So what worldwide people have said is that this is the safe model, the linear non-threshold model. It doesn't explain science, but it's the model we use for radiation protection in order to get the best chance to protect that largest number of the population. Okay, so what have we learned from all of this work? From the radiation, from the Japanese atomic bomb survivors, we learned that radiation exposure can cause an excess risk of cancer throughout life. The risk often decreases with the time since you were exposed, but it never reaches the point of having no risk, with the exception of leukemia. Leukemia pops up early and it disappears and never comes back. But other cancer exposures, Japanese atomic bomb survivors are still popping new tumors from most likely from their exposure. The second thing we know is that the risk varies with age, and the young are more radiosensitive. But it's not because their cells are more radiosensitive. They may be, we don't know that. But it's mostly because they will live longer. So what happens is most radiation-induced cancers that are solid cancers pop up 8 to 30 years after the exposure. If you're 2 years old, your likelihood of making it to 22, 32 to get those increased cancers is greater than it is than if you're 82. So therefore, the risk is higher in the young because they're going to live longer, not necessarily because there's a greater risk of young cells, although I can show some data that suggests that may be true as well. There is a lot of variation in risk associated with cancer site. We know, for instance, that thyroid is a very radiogenic organ. We get cancers from thyroid very often. Pancreas, for instance, is not so radiogenic. We don't get very many cancers of pancreas in following radiation exposure. We also know that the female is more likely to develop cancer than the male. This has been extremely controversial. You can imagine, think about NASA's situation today. NASA's thinking about sending astronauts to space, and the risk in space is radiation exposure. And the greatest risk, at least right now, that we think, although there may be other risks, the greatest risk that we think right now is cancer induction. Do you say to women, you know what, you can't go to space because you're at higher risk for developing a cancer than men are? This was very controversial. I was on a committee that decided that no, we're going to make everybody protect to the most radiosensitive female population rather than eliminate women from the flight crews. As we decrease dose rate, we also decrease risk. This is a really important point. You're getting, as you're sitting, wherever you're sitting right now, you're getting a radiation exposure unless you're in a deep mine. Many mines will shield against this, but if you're not in a mine shaft right now, you're getting radiation exposure. But the interesting thing is if you got all the radiation you would get in your whole life in one pop, you would actually get really sick from radiation sickness. But because you get a little bit every day, 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 the body's able to take it. And there's some data that suggests that in fact you may need a little bit of radiation to tickle your cells every day to make them stay healthy. So that's been that's currently a lot of ongoing work using mines where there's very low exposure radiation. And then finally, radiation-induced cancers can occur. Generally, there are a few that pop up around 8 years. 12 years is the most common for solid cancers. And but leukemias are the exception. They pop up early and they disappear. And we don't know, well, we think we know why they might disappear, but that's somewhat controversial as well. So it's not just the atomic bomb survivors, but there are other populations that have been exposed as well. The US did our atomic bomb testing. We can talk about the ethics of this. But they blew up a bunch of old military vessels here in the Marshall Islands, the Bikini Atoll. Um, the the I hope it was an automatic camera that was taking this photo, because anybody sitting on this beach would be long dead from this dose, would be dead within minutes actually following this dose. And we ran a whole series of tests. We are currently paying reparations to the Marshall Islands. Here is another test called Bravo, where they blew up a a bomb here to test it, and these doses are very, very high. 30, this is a 30 gray dose. This is the dose you would die within a day or two easily. 10 gray, you're going to die within probably a month. 3 gray, you're going to die unless you're treated with appropriate care. So these people have got sick from it. Many of them, of course, got cancer years later. The ones that did survive these, but many of them would have died from acute radiation, from radiation sickness. We also ruined the environment here. The fish are no longer the same. The atolls, which are different than just plain islands, are now behaving much more like islands. So they created changes in the fishing environment there. This was all done, and we did not ask their permission to do this. We also know a lot from a few criticality accidents. I have a top secret security clearance, so I know a few more than I'll talk about here, but I'll tell you that the examples here are no different than what is in the literature. Than is the classified is no different than what we see here. So one of the first accidents that we remember was a Los Alamos scientist working in New Mexico. His name was Harry Daghlian. He suffered a radiation poisoning when he dropped a carbide brick into a sphere of plutonium. The brick acted as a neutron reflector. It brought about a mass criticality accident, and he died within a couple of days after his exposure. And so it was a significant fatality. In 1946, there was another Los Alamos scientist. And remember, these are working now either at the time of the bomb development or just after. Louis Slotkin, he had a similar kind of experiment where he got the plutonium to reach criticality. He realized what happened. He disassembled the device, which probably saved the lives of a lot of his scientists that were nearby, but he died 9 days later. There was a criticality situation in the former Yugoslavia in a town called Vincha, which is just outside Belgrade. I've actually visited this site. It killed 1 and injured 5, but the reason why this one is important to remember is this is the first time that bone marrow transplants were given for radiation toxicity. These patients were taken on a train to France. France successfully did bone marrow transplants in these patients, and actually I met 2 of them who are still alive today. In also in 1958, there was a guy, Cecil Kelly. He was working on a plutonium purification. He mixed together 2 mixtures of plutonium that should not have been mixed. It reached criticality. His final words he said were, I'm burning up," and he died 35 hours later. And it's from all of these criticality accidents that we learned about what radiation does for acute toxicity, particularly for high doses. There have not been that many high dose exposures like this. When we get high dose radiation for cancer treatment, we're getting it pinpointed to a small part of our body. These people got it all over their body, and the body couldn't take it. Here I am with one of my team members in the South Urals Biophysics Institute near Siberia in Russia. This is where they have their where they keep their archived samples. We keep our archive samples here, and we had a lot of discussion among us because it was probably one of the first times that the the Cold War experiments from the US, which were our archive, and the Cold War experiments from Russia or former Soviet Union, where there was communication between the scientists. So it was really an experience. It was written up, Nature called it Radiation Risks, Raiders of the Lost Archive, which was kind of cool. So what have we learned from these animal experiments? Again, need to show, now I'm showing you some of my own data from my own lab, but all this is showing are experiments from approximately 104,000 mice given different doses of radiation and given at different dose rates and showing what their death looked like. So this is how long they survived against their age. Normal lifespan, the longest lifespan of a mouse is about 4 to 5 years. And you can see as you increase the dose, the lifespan decreases significantly. Some conditions make it change very dramatically. Some, particularly those that are given at a low dose rate, live to be much longer. And so these data support the idea that even low doses can have some risk associated with them, like these right here. These happen to be animals that were exposed in utero, and this is another population that was exposed in utero. But there are also interesting tidbits, as I said to you before. These are also data that came from these archival studies, and I'll just point out two things. These are animals that were given, these are dogs. I have data from 24,000 dogs in my archive. These were given strontium-90, cerium-144, yttrium-91, and yttrium-90. It doesn't matter what the radionuclide is. They have different energies and different dose rates. And I want you to particularly notice these two experiments where the animals that got some radiation live longer without tumor than the controls. Now, it doesn't happen for everything. Here they lived shorter. But in these examples, they live longer. And boy, we better figure out what it is that's doing that, because it could be a benefit that we could exploit. Okay, let me move on now to talk about nuclear power plants and nuclear safety. I'm Ukrainian by background. I've been to Chernobyl many, many times. The city of Chernobyl is here just north of Kiev. It sits on the Dnieper River, which empties into the Black Sea. The Chernobyl plant was sort of very close to the border of Belarus and Russia. There was a major explosion that occurred there. Here it is from the sky. And here's the nuclear power plant. Here is Pripyat, the nearby city. And the borders of the different countries are shown here. And originally, they evacuated this area when they finally decided to evacuate, which was very long after the accident. Today, there's an exclusion zone based on where radiation was actually found that is pretty significant. How was it first discovered? The Soviet Union did not report it. The reindeer herders in Lapland noticed that they could not find lichen. Lichen are very radiosensitive. They involve two organisms living together, and they're commensals, and they died. And what the Lapland reindeer herders learned was that there was no lichen, and they couldn't figure out why. And they reported to their government, and the government then checked their monitoring, and sure enough, there was radiation in the atmosphere, and that radiation, they presume, we now know it was coming from Chernobyl, but they presumed it must be something that happened in the former Soviet Union. And in fact, I will tell you that there are lots of incidents that happen in the former Soviet Union, even now, where we find out by something in the atmosphere, not because we were told about it. And this is a picture of the power plant. It was actually this reactor here that got out of control. It's right here on the river. Radiation was dumped in the river. Radiation was dumped all over. I won't go into it, but there were flaws in the design. And so therefore, all reactors in the US that had this design were shut down. And what was done in Ukraine is they developed a mechanism to control it. They put on a lower biological shield, an upper biological shield, and poured a lot of material onto it. This area was very, very radioactive. I think I have, yeah, I have, I'll share a picture in a minute. They eventually, with funding from the European Union, they built a shield on top of it to try to encase it. This is what it looked like immediately after the accident. You can see the massive damage. You can imagine how much radiation was just pouring out from this. This is the size of this casing. It was actually designed here in the US. And it's about as tall as the Statue of Liberty. It was actually made out here because they couldn't work on the reactor itself, and then wheeled over it and then eventually sealed. And that's how it remains today. There were videos you could watch of it being constructed for a while. So what happened is the Ukrainians put a camera on a post to take pictures. So here's a picture of some of the fuel rods melting of the material that's gone in. Another empty fuel rod laying out. But the one thing to say is that the camera got degraded after a very short time in there because the radiation damaged the camera itself. Here was a picture that we took of the power plant before the top went on it. You can see why they had to put that top on. It was leaning. It was primed for another accident. The EU was worried that if this did not get contained, we could have real problems. They chopped down all the trees that have leaves because they didn't want the leaves to get radioactive and be blowing everywhere. But still, animals were going underneath. Birds were flying on top, and that's why they had to build that casing. I still think there are animals that are burrowing underneath, but I don't know. I haven't heard that officially. And here's an illegal picture I took when I was there for one of my visits, showing workers. They had claimed at that time that the plant was shut down, but they still had workers there. It is now shut down and became a very big issue in the Ukrainian war with Russia that has been ongoing, where actually the Russians stirred up a ton of radiation near the power plant. I'm happy to talk about that if anybody wants to ask. So what do we learn from Chernobyl? 28 people died of acute radiation syndrome, 19 more died later. That's kind of shocking. We actually think, most people think it's much more than that, but those are the official numbers. They are not the numbers from the from the former Soviet government. They actually are the numbers from the International Energy Association, which measures these things. So we're pretty sure they're accurate. There was an increase. What I tell you was a radiogenic organ, the thyroid. There was an increased incidence of thyroid cancer where about 10 died. Why did not more die? Because we gave them injections of more radiation. The radiation went into the thyroid, radioactive iodine, and it killed the gland. There was an increased incidence of leukemia that was expected. There was maybe a slight increase, but even those numbers are hard to answer. They expected more solid tumors. They never saw them. So that means that probably we don't know everything about radiation we should. There were certainly environmental problems I could talk about, and then huge psychological trauma. That's just amazing. More recently, what, 15 years ago, 16 years ago, 14 years ago now, we had the Fukushima accident. This was a situation where there were no design flaws. These are the exact same reactors that we use in the US. And in fact, we sold many of these reactors to Japan. So they're the same it's the same reactor. The earthquake, they were meant to be pretty earthquake proof, and they were earthquake proof, but not tsunami proof. And the tsunami came and it washed over the entire area and created major problems. But we learned something from Chernobyl, and what we learned there was how to do our evacuations better, how to have how to be able to handle it when this happened, and so there were no acute fatalities. In fact, what happened was the government decided to evacuate the surrounding areas, probably for no reason. and there were more people that died in the evacuation than would have been predicted from the possible cancer increase. You try to move elderly out of that area in a hurry, you try to move a lot of people out, and more people died in the evacuation. This is leading people to think about how do we handle evacuations in the future. Here is Fukushima. It still is dumping radiation in the ocean. The Japanese government asks for permission every time they have to have a release of radiation to the ocean. They can control it now, at least to some extent. The ocean is dilutes it very much, and so in this area it's very concentrated. But by the time it comes to the U.S., it's pretty dilute. So in nuclear power accidents around the world, how many people have died? From Chernobyl, it was 39. There was another accident in Japan in an area called Tokamura. I didn't have time to talk about that accident, where there were 3 fatalities. For Fukushima, there were none. Other radiation injuries prior to 1950, it's probably about 15. I'm including classified numbers there. For the increased cancer incidence, it's normally a predicted number. The increase is considered to be 5% per sievert, but most of our exposures are 0.1 sievert or less, which means that it's 0.5%. If you think about what the risk of cancer overall is 25%, it's not adding that much to the increase. And relative to other injuries, deaths from exposures are generally pretty low. And I'm not trying to say we we don't talk about these exposures. I'm just trying to say they aren't as great as I think many of the much of the world would have believed. Okay, we have learned a lot about safety. I have these placemats from the Department of Energy that show orders of magnitude, 0 to 1 millisievert. Where's our natural background? It's right here at around 3 millisievert. So this is less than our natural background. This is what we set as our dose limit for the general population. In 3 millisieverts is where we're getting most of our natural background. I know I'm talking in terms, 3 millisieverts per year, but it gives you an idea of what you're getting exposed to this moment. This is where most of our CTs and X-ray scans come in, and these are the doses for those. So here's a mammogram. It gives between 2 and 4 millisieverts. That's about not, if it's 2, it's not even what we get in a year for our natural background. There are some areas of the Earth's crust that are very radioactive because they have lots of uranium. Here's one in Brazil, Ramsar, Iran. I visited one in China just back in December. Those are higher than our natural background. Here's Ramsar, Iran, 200 millisieverts per year, and we're at a natural background of 3 millisieverts in the US. But you know what? This area of Iran actually has a lower cancer incidence than many others. So it suggests that maybe having high radiation isn't the most important feature. And as I said before, in US, our cancer risk does not track with radiation exposure. Nevertheless, there are populations that have been exposed to high levels, and this is the area where we do our cancer epidemiology, trying to understand human exposures and what happens. What can we expect for acute toxicities? We have to be up here in this higher range in order to see acute toxicities, which might include a redness to the skin, loss of hair. The dose when 50% of the population dies is up here around 8 sievert, 10 sievert. And then the doses we give to patients are these very high doses, but they're given to a selected part of the body, not to the full body. So this kind of gives you an overview of what we think about. We come back to that diagram I'd shown you already, and so our problem is we still don't know what's going on at these low doses. We do know that high doses come with a cancer risk. We know there's some cancer risk at low doses, but there are other things going on, and there are mechanisms that happen at low doses that do not happen at high doses. So this area is still being studied. I had the chance to visit Niška Banja, which is a radioactive spa in Serbia. And here's Hotel Radon, where you can see grannies going in to get her weekly spa treatment, which is soaking in a radioactive spa, radioactive water. Now, what can I tell you? Granny probably doesn't have to worry about an increased incidence of cancer 20 years from now. But these kids might have to, and therefore knowing the risks is important. Radon is very different than other kinds of exposures, but it still comes with a cancer risk. I'm not sure this is so healthy for these kids, although, a lot of work needs to be done. So there are two principles for radiation biology. This is one, which is called the linear non-threshold model, linear non-threshold, which means that we don't allow people to be exposed, even a low dose. If you can avoid it, you stay away from it. It's not good for you. The second principle is what's called a LARA, as low as reasonably achievable. This is what operates in the workplace. It's the philosophy for radiation protection, and it means that you limit your time near a source, you increase the distance from the source, and you place shielding in the path of the source. Now, what has happened recently, and the reason why I think this is important for me to bring it to your attention, is that Microsoft is trying to resurrect defunct reactors at many locations because AI needs power. The 3 Mile Island reactor, which was decommissioned years ago, is now being brought back. Google is hoping to build small modular reactors even in cities like New York and Chicago to help deliver the progress of AI. That's how they're shaping it. Data centers have doubled and all require large amounts of energy. A single ChatGPT request uses as much as 2.9 watt-hours of electricity. Multiply that by millions of requests per day, and the power use goes up dramatically. The AI use outpaces anything that we can possibly gain by improving efficiency. It's predicted that generative AI could require 40% of the energy needs in the US. Nuclear power needs to scale up. If nuclear power is going to scale up, it needs to be done safely and following guidelines. So what happened a few weeks ago? Idaho National Lab produced a document. I read the document. It was sent to me not officially, unofficially, and it was a proposal to eliminate ALARA and LNT models from use in all U.S. nuclear energy industry. So we would no longer worry about being as low as we possibly can. That's reasonable. And we would no longer apply the LNT model for radiation protection. There is a scientist who I have been arguing with for decades now, who has a publication in Science claiming that there was a fatal flaw in the atomic bomb studies that were done in 1950. 50 of us radiation scientists, I was one of them, wrote a rebuttal which was accepted and published in Science, arguing that it's not just that one study that decided, first of all, that study was not flawed. But second of all, it's not just that one study that backs this, it's huge volumes of data. Oversight of the Nuclear Regulatory Commission is being changed to the Department of Energy. What does this mean? This means that the group that sets the regulations, the Department of Energy, and the commercial user are tied together. That was never allowed before. We always had a wall between the regulator and the user, no more. And congressional leaders are noting that it's a conflict of interest and claiming it should be illegal, but I don't know that that's going to stop that. There are just too many documents coming out that claims that this is safe and it's okay to do it. AI demands large amounts of nuclear power, and creating the idea of moving nuclear power plants closer to urban settings can be, I think, dangerous in the absence of appropriate guidelines. So these are my concluding thoughts. The risks of cancer from radiation exposure decrease with dose, but what is the risk at very low doses? We need more work to define that. We currently follow linear non-threshold model and ALARA, and I think that's why we have so few radiation accidents today. Are low doses of radiation beneficial? Yeah, probably they are. But if they also come with the risk of cancer, do you think we should be advising people to go get a little bit of radiation because it's good for you? We currently have safe guidelines for the use of radiation. We have no determination about what would happen if we had a rapid change in these guidelines and how it would impact safety. There's been no analysis done of it, no study done to say what would happen if we changed our dose limits. So in my opinion, more work is needed, but it's way premature to be making changes to the guidelines, and who knows how many workers are going to be unsafe. Finally, let me point you to my lab website, Northwestern University Radiobiology Archive. It's this website here. And you can go there and find tons of my lectures. I actually have 30 lectures that I give to residents that are on there. We have our data that are open. All of our data are available for anybody to take a look at. And so it might be sort of fun to play around with some radiation data. And with that, I'll end. Thank you for listening to me, and I turn it over to our respondent.
Yeah, thanks, Gayle. That was really informative. Before we get to our respondent, I'd like to remind everybody to put your questions, click the Q&A button and put in your questions, which we'll get to after we hear from our respondent, who is David C. Perry. He's the education director of the William J. Perry Project, an initiative founded by his father, former U.S. Secretary of Defense William J. Perry, to raise public awareness about nuclear weapons and reduce the threats they pose. In this role, he has helped develop educational resources for students and the public, including animated nuclear nightmare videos, 2 Stanford University online courses, and the At the Brink podcast, where he served as co-editor and writer. Previously, Dr. Perry was a professor of pharmacology and physiology at George Washington University, following a postdoctoral fellowship at Johns Hopkins. He earned his PhD in pharmaceutical chemistry from the University of California, San Francisco, and studied biochemistry at Harvard University. So welcome, Dr. Perry.
Thanks so much. So, Dr. Woloschak, that was a very impressive presentation. I learned quite a lot, and especially I'm pretty unnerved by the attempts to change regulation. We see that in a lot of areas in our life right now. I'd like to share a brief PowerPoint of my own. What I want to talk about a little bit is stuff that I want to have some clips from the podcast that we created at the Brink, and in which we look at the effects of exposure to radiation through nuclear testing in particular. As you heard, I joined my father after retiring from my professorship, and so I had to educate myself all over again on a new topic, and in particular on nuclear weapons and the radiation effects of it, which we're talking about here. By the way, I just wanted to point out that my daughter Ragini Harris, who is on this webinar, was a member of the team that did this. She was our website designer for both the podcast and for the project. My other daughter, Lisa Perry, joined the project a little bit later on, and she was very interested in a new method of communication that was coming up, and that is the podcast. And she and I then worked together to create the podcast, which we called At the Brink. And we had 2 seasons of I think, very successful documentary podcast in which we covered a whole range of topics about nuclear weapons. The reference to accidents I found interesting. Our very first episode was focused on that concept, on accidents, but with the idea of accidents relating to nuclear weapons. And that's a whole frightening and interesting topic by itself. But I want to focus now on this radiation exposure, in particular, radiation exposure through the testing programs that both the Soviet Union and the United States, and also to a lesser extent France and Britain, employed doing this, especially during the 50s. The term downwind or downwinder was developed to refer to the population that was exposed to fallout doing these tests, especially from the Nevada test, but also, as we'll talk about, the Marshall Island test that Dr. Woloschak referred to.
It's helpful to understand what exactly fallout is, how we can be exposed to it, and how it impacts our bodies and our health.
The amount of energy generated by a nuclear explosion is enormous. Near the crater area, there is almost total destruction from blast and heat. And now, large amounts of pulverized debris and molten earth are pulled up into the mushroom cloud. This is where radioactive fallout is formed. The radioactive atoms produced in the explosion join with the particles of earth and debris. The mushroom-shaped cloud forms and climbs higher. It now contains billions of highly radioactive particles of matter that we call fallout. The strong winds of the upper altitudes go to work on the cloud, blowing it off in one or more directions. Gravity tugs on the particles. The larger and heavier ones sink toward the ground, while the lighter particles continue to drift with the wind.
Here's a quick primer on nuclear physics. When you split the atom, you generate a whole pile of new isotopes. How someone will be affected by radioactive isotopes depends on several important variables. One is the dose, how much total radiation they were exposed to, and for how long. Another critical factor is the route of exposure.
I'm Dr. Steve Simon. I work at the National Institute of Health, specifically in the Cancer Institute, and I've studied radiation-exposed populations all over the world. Now, external exposure, we call it gamma rays. Those are like X-rays, but they're more powerful. They penetrate your body pretty much all the way through, and all the organs receive pretty much an equal exposure from the outside.
When Barbara Kent was 13 years old, she was exposed to external radiation when she played in the fallout ash that rained down on her summer camp after the detonation of the very first atomic test, Trinity.
Photograph
As we
in the
heard in
picture
part
is
one,
Barbara Kent.
2/3 of Barbara's campmates would die of cancer at an early age. While Barbara Kent and her campmates were exposed to external radiation from the Trinity test, a larger percentage of downwinders were exposed through more indirect means.
Another route of exposure is what we call internal exposure. And it occurs when people ingest contaminated foods or water or air. It takes much longer for the process to happen. It's much more complicated because there's lots of variables at work. Which way is the wind blowing and how much food is contaminated and what kinds of foods? And did you get those particular foods?
The organ that is most associated with internal fallout exposure is the thyroid gland. Thousands of downwinders from around the world have suffered from thyroid damage or thyroid cancer, including Barbara Kent and Mary Dixon. The thyroid is a common target because of iodine-131, a radioactive isotope created in large quantities in nuclear fission. Iodine-131 is particularly treacherous for two reasons. First, iodine is necessary for the body to create thyroid hormones, so any form of iodine that you ingest is readily absorbed into the thyroid gland.
It is one of the few elements that our body actually needs. Our thyroid gland requires iodine for proper metabolism. So here you have a radioactive form of iodine, and your body cannot tell the difference between the radioactive form and the non-radioactive form.
The second reason radioactive iodine-131 is so dangerous is that it's water-soluble, meaning that it can pollute rain, contaminate watersheds, and what is probably the most insidious source of fallout exposure, milk. When fallout is deposited on grassland, which is then eaten by grazing cows, the iodine-131 becomes concentrated in the milk being produced by those cows. The same process occurs with nursing mothers who ingest fallout-contaminated produce. This is known as the milk pathway.
So you mentioned Mary Dixon in that reference. This is a picture of Mary, and the map shown here is created by the National Cancer Institute, and it shows the radiation exposure downwind from the Nevada test sites. And since the prevailing winds in the United States are generally from west to east, you can see it's west and northwest of Nevada. But as far east as New York had significant exposure on a number of tests.
One thing that I always say is that the Cold War had casualties. We were casualties. Nuclear testing did not prevent nuclear war. It was a nuclear war.
Another category of people who were exposed to nuclear fallout were our servicemen. Tens of thousands of soldiers and sailors were required to participate in nuclear tests for a variety of reasons, including at the nuclear test site in Nevada, as well as in the Pacific in the Marshall Islands. This is a testimony of Bud Ford, who was served on the USS Boxer during Operation Hardtack in the Pacific.
It was terrifying. The heat was so bad that it turned the back of my uniform like somebody had been on it with an iron and scorched it. There was people screaming. There was some people that went blind. People were running and yelling because it was so hot. We thought we were going to burn up. You can actually see the bones in your hands when it goes off. People said they would see rows of skeletons.
Len Alcalay was a anthropologist who did his Peace Corps work in the Marshalls and stayed on to advise
What
them.
happened to the Marshallese is the best representation of the possible impacts of a modern nuclear attack.
So beginning in 1946, we tested 67 atomic and hydrogen bombs at Bikini and Eniwetok atolls from 1946 to 1958. But these bombs were huge. It's estimated that if you actually were to, divide them out over the 12 years, imagine 1.6 Hiroshima atomic bombs being exploded every day for 12 years. That's how big the megatonnage was at Bikini and Eniwetok. That's what we did to the Marshallese.
This Bravo shot, 15 megatons, 1,000 times greater than Hiroshima or Nagasaki. You have to put it in perspective. Takes 3 islands in Bikini, vaporizes them, sends them 100,000 feet into the air in this huge, highly radioactive cloud, and it drifts over onto the Marshall Islanders living in Rongelap and Utrecht and some of the other Western atolls, and it snows. And the kids start playing in this stuff. And within no time at all, they start getting radiation burns. What happens is your hair starts falling out, your skin starts to peel off. So after that, you would think, okay, we had this big accident, this horrible thing. Gee, maybe we should slow down or stop. But the testing of hydrogen bombs went on for 4 more years.
H-bomb tests exposed the Marshallese to some of the highest doses of radiation ever experienced by any population in the world. Dr. Sheldon Ricklin, a Marshallese physician and medical researcher now based in Arkansas, describes some of the horrifying health consequences suffered by many across the islands in the years that followed.
People losing their hair, kids coming in and they have beta burns around their skin, folks who actually had what they would call jellyfish babies, or babies that were born with a missing skull, or conception products that look like grapes. Those kind of things. Those are the immediate and sometimes even chronic conditions that even some of the folks from the different atolls are still giving birth to these unfortunate things that we see. But, radiation affects the body in all different ways, and not just physically, but also mentally and spiritually, and of course, culturally.
Okay, so that's all I've got to say on this. If you have more questions, you can go to our website at thebrink.org. All the podcast episodes are there, or as they like to say, wherever you get your podcast. And so I guess it's my job now to start the questioning. I had a lot of questions that I could have asked, but the one that occurred to me towards the end was, Dr. Woloschak, you were talking about this massive increase in power that's going to be needed to power the AI. And it seems pretty clear from what I've been reading and what you said that nuclear power is going to be a big part of that. What can you say about these new designs of nuclear reactors, the so-called 4th generation or small modular power reactors? Are they significantly safer? Are they better?
They are a little bit safer, but they haven't been as well tested as they should be. David, first of all, I need to say thanks for your presentation. Steve Simon is a good friend of mine. He and I have worked together on committees, so I know him really well. He does more of the physics and I do more of the biology, so we work well together. But there needs to be probably more testing of it. Canada especially has gone into these small modular reactors. I suspect that we are going to do the same thing here, but Canada too is saying, look, you can't just go put these in the middle of, a big city. You really have to go do studies on it and make sure that it's as safe as it is. I was on a committee that visited a large number of our nuclear power plants here in the US and asked how much release do we get? And today probably in the 1950s, 60s, when the first ones were being done, they weren't that good. But now there's almost no release of radiation. So they're pretty safe from that perspective. I think that's going to be the same thing with these small modular reactors. There probably won't be much release. The main thing is, what are the chances of an accident occurring with them, which is how we've gotten some of our, kind of nasty exposures now. And especially if it happens in, in an urban area, that can be very, very damaging. There hasn't been that much work that's been done on it. Now, we do know that submarines use small reactors, very safely. They've used them for years. When we talk about going to Mars, we're probably going to take these small reactors, but the modular reactors are a little bit bigger than that.
Why are they proposing to put them in urban areas? Is there
Well,
any reason
because
for
where
that?
are most of our AI power centers located? Almost all of them are in cities, or they're affiliated with universities that are in cities. So, to put them in a rural area means that people would have to travel a lot to go to work, which has become less popular now. So I think that's one of the drivers that I've been told. I haven't seen it published. So.
Okay. Actually, I have a comment of my own. I think wouldn't better transmission lines help the ability of putting power plants further away from urban areas?
Yeah, it might. There certainly has been discussion about it, but the farther away it is, the efficiency goes down no matter what you do. So
Right.
they argue that efficiency is probably not going to be enough to, that it'll take a lot away from it, is basically what the idea is.
Okay, so now some questions from our audience. Nancy Weiss-Fried asks, so what about the storage of the nuclear waste from
Yeah,
power plants?
yeah, I'm so glad somebody asked about that because the problem, so obviously our biggest worry is that we are storing our nuclear waste in most examples still in our in the nuclear facility where it was generated. There was the talk of having Yucca Mountain and everything else, but they've not been able to find a good storage space for those. So our facilities here in Illinois, I've visited 7 facilities here in Illinois. They're storing the waste and they're not storing it in places where it was intended to be stored long term, only for short term storage. So I think it's a big problem, and I think it needs to be recalibrated what we're doing. The thing is, there's something you can do to get rid of the waste. If you take, I used to do a lot of work with neutrons. If you bombard the waste with neutrons, you will eventually make it become non-radioactive. But it's very expensive to do that. So we have to think about how we want to spend our money and give technology a bit of a chance. Sometimes we develop things faster than we get something better because we pushed ourselves to do it. I mean, I remember we were sequencing the genome and everybody was estimating it was going to be like 100 years, and then it became 40 years, and then it became 3 years. And it's because we pushed the technology. Well, maybe if we pushed that technology, it would help us. But I was sitting at Argonne National Laboratory where I used to work when the Secretary of Energy came in and said, we are not going to work on that. And that was it. It's not worked on now.
Okay, another question. Kevin Powell, given the claim that the Cold War had casualties, is there an estimate of cancer deaths due to fallout compared with hot war deaths?
Yeah, people have been trying to do those estimates, but the problem is they're approximations. So we determine risk based on dose. And wait, let me just say this. So you can't tell that a cancer has been caused by radiation. There's no special marker. There's nothing that says, oh, this is a radiation-induced cancer. So right now I'm working with a guy who was exposed as part of the Marshall Islands, and he wants the military to pay for his health care because he thinks his cancer came from his exposures. And there is no way I told him I can do molecular tests. It won't answer. There's nothing that answers that it was cancer that was caused by radiation. The only thing we can do is say that there are certain kinds of cancers that are more radiogenic. So in his case, he actually has meningiomas, which are small cancers in the brain area, in the covering for the brain. And that is radiogenic. So I actually wrote to the Veterans Association and said, look, you guys, this is the best proof that it's radiogenic, that was caused by radiation. The type of cancer that it is. Nothing else is ever going to work. They did finally give him his insurance. He sent me a giant fruit basket to say thank you. But the point of it is that we don't have a way of knowing for sure that a cancer has been caused by radiation, and so therefore the risks are all approximations. They're not actually provable. But it's just like Utah, which is one of the downwinders area where they were exposed for the atomic bomb. I mean, the cancer incidence in Utah is lower than it is in most of the rest of the country, but it's probably not because of radiation. It's probably for other, because not as much smoking, not as much drinking, healthy habits. So.
Yeah. Okay. Then we have a question from Ann Stillwater about Ukraine. I guess you would comment. I believe it was about Chernobyl, if I remember.
Yeah. So I do quite a bit of work with Ukraine, and what happened during the early parts of the war in Chernobyl, I mean, to me, this was amazing. The Russian military went in near Chernobyl and they dug up what's called the Red Forest. Well, the Red Forest is an area where they had buried a lot of the radiation remnants from Chernobyl, like leaves and animals and all kinds of other things that were very radioactive. And they put it under a layer of dirt so that people would not be exposed to it and it wouldn't be flying around in the atmosphere. Well, the Russian soldiers came and nobody told them apparently that was radioactive. So they did no groundwork in preparation for that part of the invasion, and they created giant ditches and actually were living in them like trenches for a month. And then they started to get super sick because they were living in radiation that was higher dose, and they actually had to send them back to Belarus, where they had an old hospital that dealt with radiation from the Chernobyl accident. Chernobyl's been closed for a long time now, but the waste is still there. There are a lot of problems still there. That's not a place you want to stir up. And then there's the plant in Zaporizhia, which is I work a lot with the IAEA, and they have repeatedly talked about dangers of exposures that may be coming from Zaporizhia plant, which is one of the biggest nuclear power plants in all of Europe. That plant has been bombed. It has been they've put workers in there who are not trained. They've made them work at gunpoint, which is it's a very stressful job to work in a nuclear power plant. One of my lab workers is a refugee from Ukraine, and she's from Zaporizhia area and has a lot of communication with them, and people there are terrified. So.
Okay, well, I actually have another question. Speaking of, I was thinking of 3 Mile Island, the idea of restarting it. And of course, this is maybe the other end. As I understand it, there were not even injuries.
No, there were no casualties, there were no injuries, but what did happen was had that accident, had it not been caught very, very early, it would have been massive. Okay. It was only the ingenuity of the people working there that stopped the problem. If ever you get the chance, the Chernobyl series that was done by HBO, the first 3 parts of that series, there's a lot of garbage in there, and the biology is not good. But the last episode, which talks about all the things, all the flaws that happened, all the mistakes that they made for that power plant, it led to most of the problems that resulted. Well, 3 Mile Island, they handled a lot of that early stuff very well, and that's why they didn't end up having a massive problem. There were no design flaws there either, but I think they kind of let it go defunct, and to resurrect an old one is going to be hard.
Okay.
And remember, computers and stuff are like way different now. I mean, technology's changed a lot. I'm sorry, Dave.
I'll jump in and make the comment that the concept of accidents is always a fascinating one to me. Among other things, accidents happen all the time. People make mistakes all the time. And guess what? Computers are operated by people and they make mistakes. There's been, as I referred to earlier, a number of incredibly scary near misses in the nuclear weapons field, several in the 80s, including one in 1983 in Russia, in Soviet Union, where a Soviet colonel personally intervened. They called him the man who saved the world. This guy, they had an alert that they were being under attack, nuclear missiles, and it was a failure of a detection system, but they couldn't find any mistakes. But he was just convinced that it had to be, and he overread the protocol and he followed through. But if he had followed a more standard traditional Soviet protocol, they probably would order retaliation for a non-existent strike. Mm-hmm. If you all recall the Hawaiian incident several years ago, where somebody's set off we're under attack by mistake. That was not a risk of war accident, but it certainly highlighted just how systems can be easily, and people make simple errors and they can be compounded. So and now we have the rise of AI. Clearly AI is going to become increasingly a part of command and control in some ways. So I don't know how much we should be worried about that. I personally am, but
yeah. A couple more questions, see if we have time. For Paul Carr asks, what about reprocessing nuclear waste to use to power, I guess, next generation reactors?
Yeah, the problem is when it's called waste for a reason. So what happens is it goes through radioactive decay, and when it's decayed down, it can't go back. That was actually one of the problems that we had when we were building the first bombs. Is we were hoping that you could reuse them, but you couldn't. The first, if you get the chance, it's really cool. The first reactor, there were several small reactors. There was a reactor here at University of Chicago. There was another one at Oak Ridge National Lab. But the very first reactors that were used to build the bomb are in Pacific Northwest National Lab. And they have a museum there where you can actually go into these old reactors and see. And it was totally unidirectional. You could get the plutonium from the uranium, but you couldn't go the other way.
Okay. One more question. What about the mining of nuclear material? And I guess maybe the processing too.
Yeah, so there's been a lot of work done. It's not just, so uranium mining, uranium's not just used for nuclear material, it's used for other things too. I mean, and we have uranium mines. There have been a lot of people that have studied uranium miners and have looked at their lung cancer incidence. So the story with uranium is a little different than it is for other kinds of radiation. What happens is uranium makes the kind of the radon byproduct. So it makes radon, among other things. You breathe that in. It emits a type of radiation called an alpha particle. An alpha particle could only irradiate a short distance. So if you get uranium on your skin, you wash it off, it's all gone that day, down the drain, no more. And it doesn't do that much damage in a day. But when you get it in your lungs, it gets trapped in the lungs and it stays there. And so that's why uranium miners have a higher risk for getting lung cancer than other people do. But what is even worse is if they smoke and work in a uranium mine, the risk goes way up. It's way higher than smoking alone or being a uranium miner alone. So the miners have been studied for a long time. They continue to be studied. There are more safety processes in place now, but it still is a risky business.
Okay, JD, maybe I'll let you take it out, and then Maynard, I believe you have a comment.
Yeah, my comment is just real quick about just a clarification about 3 Mile Island. There are actually 2 reactors on the island, and the one that had the big accident in 1979. By the way, 3 Mile Island is just a couple miles from where I sit, so that's why I'm chiming in here. It's the other one that wasn't severely damaged that they're trying to recommission and bring back.
Oh, okay. Thank you for saying that, because the 2 articles I read said it was the same one. So
It's the same island, it's the same plant, but
no,
they
they
have
told me
two
they said it was the same reactor. So I'm glad for that. I'm glad you
Well,
corrected that.
I may be wrong, and I sure
Well, I'm sure the locals are going to know better than than the others do. So
Thank you, Gail. That was just amazing. And David too. Very informative.